Welcome to the second session of today. The session's title is Zero Emission Buildings. We have four speakers in this session. The first of these speakers is Professor Halime Paksoy from Çukurova University. I would like to leave the floor to this distinguished speaker, but also ask her kindly to present herself briefly. Thank you. The floor is yours, Professor.
Good afternoon. Thank you, Professor Çakan, for this introduction. I'm Halime Paksoy from Çukurova University Chemistry Department. I'm a professor here since 1992, so I'm one of the oldies. I work on thermal energy storage, and today I will present you solutions for zero emission buildings based on thermal energy storage with latent heat storage systems. I will share my screen. Can you see my screen now? Okay. Yes, latent heat storage applications for zero emission buildings is the title of my presentation. I would like to thank TTMD for inviting me to give this presentation. It's an honor for me. I will start with an introduction about current energy situation regarding buildings and what thermal energy storage and latent heat, specifically thermal energy storage is, and some zero emission buildings integration and applications possibilities. I'll talk about two case studies from Turkey and conclude with some remarks and future outlook. So if we look at the building sector, we can see that about 1/3 of global carbon dioxide emissions comes from buildings, and 26% of this is from building operations, and 7% is from embodied emissions, which is the topic of this conference. That is the production of materials used for their construction, like cement and steel. And if we look at the graph on the right-hand side, we can see that to reach the 2030 targets, we still have to reduce 50% of the carbon dioxide emissions. And moreover, the carbon dioxide emissions are related to the energy used per square meter or energy intensity. And here on the graph, you can see that the values are a bit decreasing trend, about 6% improvement since 2015. But again, it needs to fall a further 35% by 2030 for net zero emission buildings. And an important point here is buildings energy use are about half of it coming or for heating and cooling. So we need to integrate new solutions with new alternative energy sources now, which emit less or almost zero carbon dioxide. Another important factor is the price of energy, which is affected by geopolitics. We have to stop using crude oil, natural gas. I'm not talking about coal, that's already very bad, because these prices are out of our control. As you can see, OPEC embargo starting with that and going to war in Ukraine and recent developments in Middle East all affect the geopolitical, affect the prices, which makes us in a difficult situation from time to time, and we need to find secure and independent solutions now. So actually the solutions are there. Solutions are in the nature. First and above all is solar energy, primary natural energy source, which heats the ground, air, and water, and makes them a natural source for us. The problem is there is a gap between supply and demand of these sources. So we have to close this gap, and thermal energy storage is the main technology for that. Here on the right-hand side, you see a temperature distribution over the year. That's monthly average distributions. And in the summer, there's a peak, as you can see, and in winter, they have the low temperatures. But if you can store the thermal energy in the summer months and transfer it to winter, that would be perfect. And that's what thermal energy storage is for. It can avoid intermittence, and it can also be used for seasonal and daily variations, and can come in different sizes of capacity, watt hours to gigawatt hours, and different powers from watts to megawatts. There are three types of thermal energy storage technologies that are in use today. Sensible heat uses temperature change of any material with a storage capacity around 100 megajoules per cubic meter. Latent heat thermal energy storage uses latent heat accompanying a phase transition of a material. And here we have higher storage capacities than sensible heat. And the last one is thermochemical using enthalpy over reaction or absorption process, which has even higher storage capacities up to 1,000 megajoules per cubic meter. And today I will talk about latent heat thermal energy storage applications and opportunities for net zero emission buildings. With latent heat thermal energy storage, you need phase change materials that undergo phase transition. You see here the possible phase transitions a material can undergo from solid, liquid, gas, and even plasma. And there are also solid to solid phase transitions between different molecular structures. And from these phase changes, we are focusing on two of them for latent heat thermal energy storage. That is melting freezing between solid and liquid, and solid-solid phase changes. The materials that can be used as PCM, actually all materials undergo phase changes, but we have to have the right melting temperature and right melting enthalpy. In this graph, you see melting enthalpy versus melting temperature, and there are different classes. Below 0 degrees, you see water at 0 degree, of course, and water salt solutions below that. And above 0 until 100, there are paraffins, salt hydrates, and some sugar alcohols at higher temperatures and so on. But in this narrow window here in the blue area, you see building applications. Depending on what type of thermal energy storage you are using, it can be around 0 for cooling, or depending on your source, it could be up to 50, 60, or even 70 degrees Celsius. So you need to know what your energy source temperature is and what the requirement of the building is to decide on that. There are some commercial PCMs out there. Here you see a picture showing different companies and their products. And they are listed here according to their melting temperatures on the x-axis and volumetric heat capacity on the y-axis. And the building applications window is shown here. So you can see there are many materials out there. The way to integrate latent heat into buildings are basically divided into two: active active systems, which have to use heat exchangers with a heat transfer fluid, for example, like this one, a small one shown here. And here you need to have additional equipments like pumps or fans to circulate heat transfer fluids. The second one is the passive latent heat thermal energy storage, where PCM is added in building materials like concrete, plaster, or building elements. And thermal energy is naturally collected by these elements. And here you see the microencapsulated form of a material that's shown in the same image here. It could be different macro or micro sized or shape stabilized forms of PCM that are used for passive applications. So how do we use these in buildings? I'll give some different classifications, starting with building materials and structures that I have just shown. As I said, they are incorporated in building materials and elements and absorb the excess heat, the solar radiation during the day, and release it at nighttime. So you see in the picture here, the schematic showing of during the day and nighttime operation. And the materials can be gypsum boards, concrete, insulation, structures, walls, ceiling, floor, windows, roofing. And what benefit PCM brings in these applications is shown in this graph here. For a delta T of 10 degrees between inside and outside of a building, 1 centimeter of PCM is equivalent to more than 10 centimeter of brick as a building material, or more than 30 centimeter of gypsum, and I'm not going to tell the others. So it saves material, but also makes solar radiation from today available to be used for heating at nighttime. Other applications, number 2 in this case is solar energy, and solar thermal storage can be done for heating and domestic hot water demand, and also for powering HVAC systems during non-sunlight hours to reduce reliance on the grid. So here there is a schematic picture showing a flat plate solar collector and a PCM filled in the heat exchanger, or PCM heat exchanger in the tank. There are also applications, more recent, for PVT collectors that are used for dual purpose, increasing efficiency of electricity generation of PV panels by reducing temperature and capturing heat at the same time. So you see here a small picture showing PV panel with a coil at the back that would cool down the PV panel and also extract the heat that is given off from the PV panel to be used for heating purposes in the building. For solar applications, you need to use different types of heat exchangers depending on what your space is, what is available, and here you can see different heat exchangers with fins that have been studied by different researchers. And on the right-hand side, you see a picture of a pack bed where PCM is used as packing material, and these are transferred either through water or other types of heat transfer fluid to the user and also to the heat source. You can also couple solar thermal storage with floor heating, which is very popular in some European countries right now. Heat pumps are also benefiting from PCM integration for higher efficient operation and increasing the versatility. For example, integrated with air source or ground source heat pumps, or hybrid heat pumps to store excess heat or cold for domestic hot water. Heat pump coupled for district heating to supply heat to multiple buildings, or combined heat and power systems, modular heat pump systems to integrate with smart grids and to pair with building energy management systems, and also advanced control systems for predicted heating and cooling loads, electricity prices, and weather conditions. So you can have the picture shown here as seasonal storage with the borehole storage, underground storage, PCM storage, and a series of houses. This is actually from Drake Landing Solar Community in Okotoks, Canada. You can go online and see how much energy is produced and made available to the buildings. And here you can see different ways of integrating thermal energy storage in a heat pump operation with different components. Cold storage is another application, and this could be done in a number of ways. One is shown here with a product from Climator. It's called Cool Deck, and this PCM, including ceiling, suspended ceiling, is added to the building's suspended ceiling, and during daytime, heated air moves up and melts the PCM, and nighttime, the freezing PCM would release its heat. So that would allow the room to be passively, but with an additional fan power to be cooled down. Nighttime radiation cooling using solar thermal collectors. I will talk about that in the case study, so I will not mention it here more, but also we'll talk about peak shaving or load leveling with ice storage, which is another type of PCM, shown here with ice on coil, ice slurry, and encapsulated ice type. This type of storage is using off-peak hours, nighttime electricity prices, to store cheap cold and release it during the day when cooling demands are higher and electricity prices are lower, higher to storage. I will now talk about the first case study. This is called Green Refuge System. It's a project that we have been doing starting with a British Council TÜBİTAK project. Now it is an Aeronet project. Here you see a cabin with solar collectors on the roof and some tanks for storage of PCM and fan coils. The operation is for heating. During daytime, solar heat from thermal collectors is collected, and at nighttime it's recovered. And for cooling, again, these collectors are used for nighttime radiation and daytime recovered for cooling. So here we have a test cabin of a floor area of 20 square meters. It is meant to be used for refugees and also disaster relief housing. So the size is according to that. And we have 8 flat plate collectors on the roof and 2 tanks, each having 1 ton of PCM, paraffin for hot storage, and coke oil for cold storage, and 4 fan coils. The system is automatically controlled and monitored. And in winter operation, you see the collectors with a slope that is suitable for Adana climate. This is located in Adana, where we are, and collecting solar energy during the day for winter operation. And at nighttime, the network for recovering the stored energy from the hot thermal energy tank to the fan coil is opened, and shelter is heated. And for cooling, please notice that the fan collectors are now in horizontal orientation, allowing nighttime radiation, cooling, capturing cold from summer nights and storing it coconut oil. And then we are recovering that during daytime to cool the shelter again through the fan coils. Here I would like to show you some temperature measurements. We are doing many measurements for PCM tanks and inside and outside of the cabin. And this is for heat storage during the day. You can see PCM is melting and then freezing during recovery. And when it freezes, it gives off its heat to the ambient. And by doing that, the inside temperature is kept about 8 to 14 degrees above the nighttime outside temperature. So the energy savings, economics, and carbon dioxide emissions are shown here compared to different sources using electricity, coal, and natural gas. And these are figures from last year, so the prices may have changed a little bit. But all in all, if we use the systems with 50% efficiency, which is a moderate one, we have higher efficiencies so far. For the existing, the shelters in 30, which is 30,000 plus, we can have 70 gigawatt hours per year from heating and 20 gigawatts per year from cooling energy savings. The second case study is about thermal enhancement of concrete mixes using PCMs. And here we have also worked with a TÜBİTAK funded project for developing microencapsulated PCMs from bio-based PCMs and with a building oriented temperature, melting freezing temperature. And we wanted to have long-term stability and a good compatibility with building material in terms of distribution in the material and also mechanical strength. And then this developed material was added to prefabricated panels and used in test cabins. Here in the same picture, you see the microencapsulated PCMs, little spheres mixed with the concrete and they are intact and stable when they're mixed with concrete. When we are developing this material, we have a 3-step basically with several sub-steps. But the first step is forming an oil and water emulsion. The PCMs are usually oil-based and they are not soluble in water, so you need to make an emulsion. Then you have a polymerization reaction with different requirements of temperature, time, and mixing conditions. And at the end, you have a powder. First, it's in water, so you have to wash it and then filter and dry. And what you see in the same here is the result. Then we formed a consortium with our prefabricated panel producer in Adana, Kambeton. They produce these panels that you see, and they have an automated fabrication method. We determined the dosage of microencapsulated PCM to be 10% based on the mechanical strength calculations and tests we have done. And then we made some test buildings with these prefabricated panels. 3 test buildings without PCM, with PCM, and in microencapsulated and bulk forms were used, and long-term monitoring and environmental economic assessment was done. Some results from this monitoring, you can see that the maximum peak was delayed by about 1 hour in summer. Load shifting was achieved, and also maximum delta T's was lowered compared to the reference building, about 2.2 degrees, which corresponds to about 11% energy savings. Some interesting thermal camera images may show how PCM really works in these systems. This is taken at 12:30 p.m. Noon time, and the cross section is showing the first picture on the left, showing the concrete panel, half of it without PCM, the second half with NPCM. And on the right-hand side, you have only concrete panel without any PCM. If you look at the thermal camera images, on the left-hand side, the first 6 centimeters through the concrete, the solar radiation passes through the concrete with some delay, but compared to the second half, second 6 centimeters, you see that there is a retention of heat. The thermal mass that is introduced through the phase change material slows down the heat transfer and stores the heat. So the outside temperature at this time was 35 degrees, and inside temperature is measured as 20.5 degrees, about 14.5 degrees difference. If you look at the right-hand side picture, without any PCM, you see that delta T is 7.5 degrees. So half of what we have with the PCM. So if we are able to use such materials in about 5 million buildings in Turkey, you can save about 80 million tons of carbon dioxide per year, and also some heating energy. So now I would like to conclude with some remarks. What are the strengths of these latent heat thermal energy storage systems? First of all, you can save energy in buildings and increase local and our renewable energy sources, solar energy. Shifts in peak loads are available, is it possible? Thermal comfort can be enhanced, and local energy sources will be used at low cost, depending on what type of system you are using, of course, and dependence on imported fossil fuels are decreased significantly. The challenges are easily available, affordable, and reliable PCMs in Turkey are still not available. There are many, as I have shown you, around the world, but not too many in Turkey as far as I know. And awareness on technology is limited, and qualified projects showing benefits are needed. And future outlook would be new trends from new PCMs from waste and nature, biomimicking the nature, and also new manufacturing techniques that can involve 3D printing and additive manufacturing. Multifunctional PCMs that would use solar light for thermal, electric, thermal, magnetic, and thermal conversions, and new applications that combine different sectors for multi-generation and flexibility. So making use of thousands of PCM solutions for zero-emission buildings is what we need, and we have to act now, or otherwise there will not be time left for our Earth. I would like to thank our project funding agencies, TÜBİTAK and British Council, Geothermica Joint Call, our partners in the projects, Erciyes University, NİDE, Ömer Halis Demir University, Kambeton Industrial Company, Northumbria University, Arçelik, AFAD, Royal Institute of Technology, Norce, and Pure and Kobe. And of course, big thank you for our team, and thank you for listening to me.
Thank you very much, Professor Paksoy, for this lucid, crystal clear presentation. I just have a small remark regarding the heat retention in Adana, those 3 houses. Of course, daytime is very fine, about 7 degrees Celsius of lowering the temperature, inside temperature. However, one has to look also the nighttime distribution of temperature, because those micro encapsulated pieces would also will have their share in the heating of the interior of the building at night. But nevertheless, solutions can be found, of course. This is very nice. And this is an area where my interest lies as well. So I listened to you very carefully and I learned a lot from your presentation. Thank you very much.
Thank you. Can I remark on that?
Yes, please, please.
Yes, the melting point of the microencapsulated PCMs we use is between 23 and 27. So when they release heat, of course they will release heat, but that would be at that temperature. And that's also if there is heat, excess heat, they will absorb it during daytime too, nighttime too. So it's more like balancing, and also it is mimicking the traditional buildings with thick walls. Thick walls, which I was born to in Adana, have that thermal mass. But now we are doing thin walls like that.
I see.
So PCM helps that.
Okay. Thank you very much for your comment. Now it's it's our second speaker of today, Mr. Gürson, Mr. Orhan Gürson, who will talk about water-to-water heat pump utilization for waste heat recovery from cooling towers in tire production. I will ask kindly to Mr. Gürson to present himself, and then the floor is yours. Please, Mr. Gürson.
Thank you, Mr. Çakan. First of all, I would like to welcome everyone. I also want to thank TTMD Symposium Board or Committee for giving me this opportunity. My brief history is I'm working as a partner at GMD Moscow Engineering Company. I've been working more than 25 years. I have gained experience, especially in the design of large facilities such as factories, hospital buildings, airports, and etc. The topic I will talk to you about today is actually waste heat recovery. Let me share my presentation. I hope everybody can see my presentation. Is it okay with the presentation? I know it doesn't seem very interesting at first sight when I say heat recovery. I know that because everybody knows heat recovery's importance. But today we will go over about the heat recovery systems with water-to-water heat pumps, supported by water-to-water heat pumps. We see heat recovery systems in every kind of facilities, especially air-to-air heat recovery is very popular in HVAC applications. We all know that air-to-air heat recovery is very common in the packaged units such as air handling units or heat recovery units. But today, we will talk about water-to-water heat pumps, which can provide wide range of usage for the heat recovery circuits. So we have to define first what is waste heat and where can we use it, and how can we spot where the waste heat is. We often use water-to-water heat pumps in heating and cooling applications, Of course, they are becoming more popular. And this Paksoy mentioned about the heat pumps used together with the PCM materials are very popular right now. Of course, they are more popular not only because they help reducing dependence on fossil fuels, but also because they are more efficient systems. If the outdoor air temperature is suitable, air-to-water, even air-to-water heat pumps can be used for the main heating source for the domestic heating applications, such as underfloor heatings or the domestic hot water generator. But the topic I would like to highlight in this seminar is a very different application. Here we want to focus on the use of water-to-water heat pumps to improve heat recovery systems. The primary goal in heat recovery system is to capture waste heat energy in the simplest way, make it simple. But therefore, it is necessary to investigate the initial investment and operating conditions. The most critical point is to recover the waste energy from the fluids without using a heat pump at first. If we have an opportunity to capture the waste heat without heat pump with an exchanger, for example, it would be more efficient. However, under certain conditions, if the waste heat energy is not at usable condition, such as the water temperature may be low, heat pumps will provide excellent results to reach proper temperatures for the application. So if we see the waste heat energy that we can use, we can adapt and direct to the main streamline of the heating system. We may use heat pumps for this purpose. You will be able to see the design system of the schematic, which we did for the tire factory. If we need to make a basic definition for this system, for the subject, it would be very easy to explain by drawing an analogy with a water loop heat pump system. The water loop heat pump system are used in many commercial buildings. We have faced in many commercial buildings, but the logic is very similar. There is a heat source, for example, from this process coming this heat from the source, or this can be a jewelry store in a shopping mall. If we have a source and we have enough energy coming from that source, we can direct to this heat source, not the cooling tower, and we can direct to the heat pumps as well. The waste heat source can be used as a supportive heating system for the main heating system. In the subject case, we capture the heat from the process line coming from the tire production, and which is used to cool by cooling towers. The water temperature was around 25 degrees in winter time. This was not appropriate for the main heating system temperature. There may be some areas that you can use that heat as a heat source, but in this case, we didn't have an opportunity to use this water as a main heating supply. We could provide this water up to 55 degrees Celsius hot water with the water heat pump units. In this subject, there is a process waste heat from the cooling tower that also needs to operate during winter. There is another benefit that this waste heat actually comes from the purpose of the cooling of the certain process. Using water at 25 degrees was not possible, so we had to step up. In this case, the operation of the cooling towers are less, or sometimes they turn those cooling towers off. It is one other benefit of the system. And we are adding up some more heating capacity with the water heat pumps. When we encounter waste energy and face limiting temperatures in such case, in the recovery process, heat pump systems become like a solution because we can step up the temperature up to 95 degrees. Right now, you can put heat pumps serial and cascade system. You can step up the temperature up to 95 degrees. But before we are designing those systems, we have to determine and prepare a feasibility study or life cycle cost analysis would be very beneficial. These analyses can be carried out through the simulations that cover the entire year operation of the facility. And this allows the benefits gained during the recovery process as identified above. And also sustainability studies must also be carefully examined in these analyses because during the winter time they can be operating good, but in the summertime the factory produces same tires as well. So we have to be careful about sustainability of the system. For this purpose, facility-specific analysis may be required, but through these simulations, investments can be directed to the most appropriate areas with the optimal cost. So we have to focus on the most appropriate areas to design the heat recovery systems together with the heat pumps. There are similar heat recovery systems in the commercial buildings as well, but when we encounter them in the industrial facilities, we need to be more cautious. Of course, in industrial facilities, both the capacities are much larger depending on the facility type, and the fluids can be more challenging. It can be acid or something like that, or temperature is very low. As a basic principle, by capturing waste energy and converting it into a usable energy, we make sure if it is feasible. We know that we can reduce carbon emissions while also achieving energy and water saving, but the feasibility study is a must. Otherwise, we can face additional operating costs and unnecessary initial investments. I'm going to show capturing waste heat and raising the temperature. In fact, similar situations may occur in many facilities. In such cases, priority should be taken to utilization of the waste energy. During the feasibility study, risks related to the operation of the system should not be taken, and integration issues should be investigated. Especially existing factories are more critical. The issue of continuity, which is critical in some such facilities, should be overlooked. Especially in industrial facilities, solutions should be found without taking risks regarding the continuity of thermodynamic fluids that feed the vital systems of the facility. By gathering information from the facility engineers, it can be ensured that the designed heat pump system easily integrates waste energy into the existing system. As you can see from the diagram, you can see there are two heat pumps here in the system, and the process hot water return lines that go to the existing cooling tower are directed via the cooling tower reservoir, are directed to the heat pumps. In other words, by having these two heat pumps do the work of the cooling towers, we ensure that the cooling towers do not operate or having less operating hours. Additionally, the existence of low temperature flue gas, we had a very good opportunity here. Flue gas recovery system, the heat pumps can be integrated easily. This has provided a significant advantage. In some facilities, this situation may not happen. In other words, if there is no existing low temperature system to integrate, we may need to find alternative solutions. Here you can connect the heat pumps in series to reach higher temperatures. I'm going to show the benefits of the high temperatures. But Of course, in this case, the efficiencies will drop dramatically. Therefore, a very detailed feasibility analysis is required in such situations. In some facilities, it may be necessary to achieve higher temperatures for the hot water produced by the heat pump to be used. In these facilities, you can create series type, we may call it cascade type heat pumps, and provide the required water temperatures. But as you can be seen on the diagram, by cascading two systems, you can reach higher pressures, which means higher temperatures in the heat pumps. In this case, we may face with a system that consumes more energy. Still, if your waste heat amount is large and the usage duration is long, you might achieve a good gain. So you can decide invest the heat pumps. Of course, as in all thermodynamic systems, the issue of efficiency should be investigated and examined. Especially when selecting a heat pump, careful studies must be conducted regarding the temperatures and efficiencies. You will be able to see the graph that the water temperature lowers, so the coefficient of performance is getting higher. There may be a fixed or binding temperature and flow rate parameters in existing facilities. There may be some handicaps for the existing facilities, so therefore equipment and temperatures that are suitable for these parameters should be selected. However, in newly designed systems, the water temperatures where the system will operate most efficiently should be chosen, and the selection of the end-use devices should be compatible with this one. If this is an existing facility, you have to be sure about the existing water temperatures, existing fluid temperatures. But if you are making a new design, you can choose a better temperature for the better performance. In single-stage systems, as seen on the screen, efficiencies decrease as temperature increase. Therefore, the lower the fluid temperature used on the secondary side, here you can see the lower the fluid temperature, the more efficient the system will be. However, it's also necessary to check the minimum temperature limits of the equipment. You cannot go beyond 30 degrees or lower if you are using at 25 degrees primary circuit temperatures. In the efficiency analysis of heat pumps, fluid temperatures must be monitored to ensure selection is made in the most efficient operating mode. However, certain limitations, binding temperatures cannot be ignored. Of course, the pumping cost in the system should also be considered, because we are putting a new heat pump, a new equipment, and also we are putting new pumps to circulate the water. So it must also be considered, and the impact of flow rates caused by temperature differences on the existing or new piping system must also be taken into account. When using heat pumps in heat recovery systems, the simplest possible system should be investigated. Since we will be adding additional devices, fluid pumps, control valves, heat exchangers, and automatic control components to the existing system, we must choose the simplest system. This will, I'm going to show, this will save us both in the initial investment. We are putting additional pumps, additional heat pumps, and also the operation wise, it would be beneficial. If there is more components, you may face more problems in the system. If the system is existing, there will be more problems. Of course, in existing facilities, more complex systems may sometimes be required unintentionally. In this case, suitable spaces should be found for both piping and additional equipment, and the design should be shaped accordingly. Fundamentally, recovering waste heat will naturally increase efficiency. In addition to this, by using a heat pump, we inject additional capacity into the system without relying on fossil fuels. It's good, providing solution to the energy source problems as well. The use of heat pumps presents a very good alternative for fluid temperatures that are either not suitable or not recoverable in many facilities. Recently, with the advancement of heat pump technology, flexibility in terms of temperatures has been achieved, along with the wide range of capacities. I can remember that 20 years ago, we could achieve 70 degrees. Right now, we are now 95 degrees with the cascade system. Wide range of capacities and wide range of temperatures is a good advantage. As electricity generation becomes more diversified and accessible, the application areas of heat pumps will also expand daily. Heat pump use will become more common and flexible, especially in systems that produce excessive heat, such as computer technology systems, data centers, artificial intelligence centers, or popular cryptocurrency centers. They are using more electric energy. This morning, Mr. Allard mentioned about a coal and steel treaty, which is dated, as far as I can remember, 1952. If we think about after 70 years, 72 years, in the UK, 90% of electricity was generated from coal in the early 60s, right now. But just last month, last September, they shut down their last coal-fired power plant. If we look at the near future, we may see that the signals very positive developments in the diversity of electricity generation in the coming years. While electricity consumption is expected to increase very badly, very fast, due to the system like artificial intelligence and other I mentioned before. So there are alternative production methods. Heat pumps are a very good alternative to use electricity for the HVAC field. Not only HVAC field, but also in the factories. We are visiting some factories that we can see the cooling towers are operating in winter time. So it may warn us that there's a cooling tower. If it is operating in winter time, we can capture that energy and we can use this energy to the heating source as well. So if we are talking about circular energy, we have to look the cooling towers or cooling units in winter time at first. So heat pumps offer us a wide range of solutions, including energy recovery systems to help us move away from fossil fuels. We use more heat pump units together with the heat recovery system. We can provide both eliminating the fossil fuels and also recovery energy. Therefore, we can expect them frequently used in many facilities in the coming years. That's all I have to share today. If you have any questions about topics, I'd be happy to answer them.
Thank you very much, Mr. Gürson. I agree with most of your comments that you presented in your conclusions. I have heard, if I'm not mistaken, I have heard that the electricity consumption in data centers will double in a couple of years. As you said, the crypto markets and AI is actually firing this high consumption. However, there's always good news because this heat from data centers, for example, can be used as waste heat, and there are many ways. There are various methods to use this waste heat from data centers. So that puts a burden on us, on technical people, to find clever ways, wise ways to utilize this excessive energy. Thank you very much for your presentation. Now, the third speaker of this session is Mrs. Özdemir. I would ask her to present herself briefly, and her topic is mitigating strategies to decrease the heat island effect and to improve the thermal comfort in urban outdoor spaces, which is extremely interesting. So the floor is yours, Mrs. Özdemir.
Thank you, Professor Çakan. Thank you for the introduction. I am Dr. Kalaycıoğlu Özdemir. I am an architect. My field of expertise is building energy performance, let's say. Currently, I work as a researcher in several research projects in Özyeğin University, and also I continue my work in my own company. I will share my screen. Yes, I hope you can see. Sorry. Yes, today I would like to present actually a review on heat island effects and its heat island phenomenon and its effects on outdoor thermal comforts of the citizens. Generally, how we can decrease the urban heat island effect and how we can improve the outdoor thermal comforts. We all know that the number changes, but most of the world's population lives in urban areas nowadays. And on average, people spend more than 90% of their time indoors in cities. Of course, we can understand that this causes high levels of energy consumption in buildings, and also this affects their psychological states, spending more time indoors. So people are always encouraged to spend more time outdoors. However, when they spend more time outdoors, they are exposed to various temperatures, air velocity, relative humidity, and solar radiation fluxes, which affects their thermal comfort, of course. So we can say that we need thermally comfortable outdoor spaces to spend more time outdoors, to spend more pleasant time outdoors. If we want to define the urban heat island, Professor Öke have defined the urban heat island as the phenomenon wherein the temperature of urban area is significantly higher than its surrounding suburban and rural areas. And most of you know that this is because the buildings, roads, and all other infrastructure absorbs the solar radiation during the day and then re-emits that radiation, which causes the higher temperatures comparing to the rural areas. So what can we do? Actually, before, what are the causes of urban heat islands? So we can say that reduced natural landscape in urban areas and also urban material properties. Actually, I will be go in more detail of these causes later, so I will just skip here very rapidly. But I can say urban geometry is also very much important as a cause of urban heat island because it affects the solar radiation and airflow patterns in cities. Another important cause for the urban heat island is the heat generated from human activities, which is called anthropogenic heat, actually, very or we can say. It is produced from air conditioners, HVAC systems, especially during summer period, and also it is produced in industrial facilities. And this is an important contribution to the heat island effects. And also weather and geographic conditions of the cities may affect the urban heat islands. Because calm and clear weather conditions always result in more severe heat islands, which means higher temperatures, where strong winds or cloudy weathers decrease the heat island effect. Or geographic conditions, mountain nearby, as sea nearby, or the topography itself of the city would affect the, of course, the temperature pattern of the city, so the heat island of the city. However, maybe the most important factor for the urban heat island is the human activities. Here there is a research study which collected data from 743 cities for the surface urban heat island and 988 cities for the canopy layer heat island. And they resulted that when they look at the weekly rhythms of urban heat islands, they see that during the weekdays, urban heat island effect is increased, and during the weekends, it is decreased. So they result that the human activities is the basic cause of the urban heat islands. What are the types of urban heat islands? Basically, if you study the urban heat island by the surface temperature, then it is called surface heat island. Or urban heat island can be studied within the urban canopy layer, which is the layer between the surface and the above the buildings. So this layer is called urban canopy layer. So urban heat island can be examined, can be investigated within this layer. So it is called a canopy layer urban heat island. Or urban heat island can be analyzed in a larger scale at the upper part, at the upper atmospheric part of the whole city. So in this case, it is called boundary layer urban heat island. So if we go through the outdoor thermal comfort, what is outdoor thermal comfort? Actually, thermal comfort in outdoors or indoors, it is the same. It is just the sensation of feeling thermally neutral, thermally comfortable. Actually, it doesn't matter if it's indoors or outdoors. It's just because it's our comfort. It's the people's sensation of feeling thermally neutral. However, when it is in outdoors, it actually affects the quality of the urban spaces because it increases the public health and well-being. It increases the tourism activities. It increases the use of open spaces, and also it increases the levels of social interactions. So, as I said, if we have thermally comfortable outdoors, then we can spend more time outdoors. Here there's an interesting study I would like to share with you. Unfortunately, I couldn't reach the very much details, but to sum up, it says actually if we can design outdoor circulation areas as sufficiently comfortable, thermally comfortable, then the expectations of people for indoor conditions are getting closer to the outdoor conditions. In this study, they have planned a route for a student and for lecturer. During a day, they have a different road from their home to the class, to their office, to their etc. So they have measured their expectations of comfort. And as I said, they found that if people are comfortable in outdoor spaces, then their expectations are getting closer for indoors. Expectations for indoor thermal comfort are getting closer to the outdoor conditions. I think this is very important because as you may understand also, this may be a key point for the building energy efficiency, actually, because it would affect, if we can design thermally comfortable outdoors, it would also affect the design parameters of the indoors. If we look at to the factors which are affecting the outdoor thermal comfort, actually they are very much similar to the indoor thermal comfort parameters. Environmental factors are air temperature, solar radiation, humidity, mostly relative humidity, air velocity, and radiant temperature. If we look at to the personal factors affecting the outdoor thermal comfort, again, clothing, activity level, personal health factors, psychological parameters, age, gender, body proportion, weight, even hunger can affect your sensation of thermal comfort. And also, if we are talking about the outdoor thermal comfort, of course, we have built environment parameters. But I tried to match the colors. For example, building layouts and urban canyons, which means streets. Actually, they are affecting the outdoor thermal comfort because they are affecting the solar radiation exposure, air temperature, humidity, air velocity, etc. So materials used in built environment affect the radiant temperature. Again, vegetation and water bodies also mostly affect the air temperature. Of course, they have also have effect on air temperature for radiation that I will also explain later in later slides. But these built environments factors also affect these base factors, so they affect our thermal comfort in outdoors. And there are actually, according to a study, there are 162, but I'm sure there are more thermal comfort index, outdoor thermal comfort index to examine, to measure the outdoor thermal comfort. The one that I could find first is the corrected effective temperature, which is developed in 1932 by Vernon and Vollmer. Another one, I just here tried to list the most important ones. Another important one is the wet bulb block temperature, which is developed in 1957. Standard effective temperature, which is used highly in research studies, is developed in 1971. PMV, predicted mean mode, is developed by Fanger, but it is adopted to outdoors by Jędrzejewski and Nübler in 1981. So it is predicted mean mode for outdoors. We have physiological equivalent temperature, PETS, which is developed by Höppe in 1999. And again, the Deere and Pickup have modified the standard effective temperature for outdoors in 2000. And researchers from Berkeley, they have developed Berkeley comfort model in 2001. And we have physiological subjective temperature, PCT, which is developed in 2007. And finally, maybe one of the most important indices is the Universal Thermal Climate Index, is developed in 2012. And the last one that I could find is Global Outdoor Comfort Index, which is developed by Galassi and his friends in 2018. I will just give a brief summary, some of the important indices. The first one is UTCI, Universal Thermal Climate Index. It is maybe the mostly used and highly rated one in recent studies. And it was developed within Cost Action 830. It actually compares the impacts of temperature, relative humidity, air velocity, and thermal radiation with respect to a reference condition, reference environment. And that reference environment is defined as 50% of relative humidity, calm air, and radiant temperature equals to air temperature. And using this formula here, UTCI calculates a temperature, an apparent temperature. And then by using this temperature, we can evaluate our thermal comfort level. So if that apparent temperature, calculated temperature, between +9 to +26, for example, we are thermally comfortable. There is no thermal stress. And there are, in total, there are 10 stress categories within UTCI. So above this +26, we feel hot, and below these temperatures, we feel cold. Actually, you can see on the screen the various stress levels. If we continue with PETS, physiological equivalent temperature, it is again one of the most used indices. It is developed by Höppe, and it is based on the Munich individual energy balance model. Again, in PETS, again, a reference indoor temperature is calculated by using this formula here, at which we would feel the same thermal stress as the actual outdoor conditions. So again, we have 10 stress categories within PETS, but this time, as the calculated temperature is a reference indoor temperature, so it is closer to our temperature perception. Because as you can see, between 18 and 23, we feel comfortable. So the calculated temperature is between 18 and 23, then we can say that outdoor urban space is comfortable. If the calculated temperature below, then we feel cold, and if the calculated temperature is above the 23, then we feel hot. Sorry. PMV for outdoors is again very much used in this, one of the very much used indices. It is actually more or less the same as the for PMV for indoors. So it based on the votes of the the users. So if most of the votes is 0, then the urban space is thermally comfortable, neutral. If the most of the votes is plus votes, plus 1, 2, or 3, then people are feeling hot. If the most of the votes minus 1, 2, or 3, then most of the people feel cold, we can say. Yes. PCT, again, physiological subjective temperature in this is, again, one of the most used ones. It is derived from the Mann environment heat exchange model, and it is first published in, this model is published in 1994. In this thermal impacts of temperature, relative humidity, air velocity, etc., are expressed as mean radiant temperature formed under the clothing just above the skin. And after 15 and 20 minutes of adaptation to the environment. So it is a little bit different in this before from the before ones. Let's continue. And finally, standard effective temperature for outdoors. Standard effective temperature is developed by Kage and his friends, and it represents the temperature of a hypothetical environment where the total heat loss from the skin of a person wearing a standard amount of clothing matches the thermal comfort of the actual environments. Actually, we can just sum this way. So if we continue with the strategies, how we can decrease the urban heat island effect and improve the outdoor thermal comfort. Actually here, I would like to repeat that I am presenting results of a review study. So in this review study, there are several the results of several studies. So it gives a very good picture of the strategies. What can we do to decrease the urban heat island and improve the outdoor thermal comfort? As I said before, urban geometry is maybe the most important factor. So what can we do? There are two important terms here. The sky view factor is a dimensionless number ranging from 0 to unity, representing the amount of unobstructed sky seen from a given point. The second important term is height to width ratio. It is the ratio between the height of the buildings and width of the streets. So if we talk about the compact urban spaces, then we can say they have low sky view factors and height to width ratios are high again. So it means there are high buildings with narrow streets. So in this case, you can understand that the solar radiation is really reduced in urban areas, and that creates a higher thermal comfort in hot climates and during summer periods. Also, the orientation of streets are also really affects the thermal comfort or the solar radiation exposure. Because according to a study, they have found that with the east to west orientation, the solar radiation is always, the street is always exposed to solar radiation. And if they increase the height to width ratio to 3, and it didn't improve the thermal environment, it didn't improve the thermal comfort in east to west oriented streets. However, in the north to south oriented streets, with just 0.8 height to width ratio, they can provide just thermally comfortable conditions, of course, in summer periods, because they can easily block the solar radiation. So the orientation of the streets are very important. We talked about the compactness of the urban spaces. The compactness also affects the wind effects. More compact areas decrease the wind exposure. So more open urban forms increase the exposure to the wind. And again, according to another study, the researchers found that 10% increase in solar sky view factor resulted in 8% increase in wind speed at the pedestrian level. So in another study, they studied the direction of the wind. Again, the building's layout affects the wind exposure. They found that the wind speed in streets normal to the coast, because the wind comes from the coast, reach to 2.5 meters per second, while in streets parallel to the coast, the maximum wind speed was only 1 meter per second. So also buildings are blocking the wind actually. So we have said blocking direct solar radiation in compact areas makes it cooler. And so because creating shaded areas makes it cooler. Also, we should say that if, for example, if we have compact urban forms to increase the outdoor thermal comfort in hot climates, then it will be, we should know that it will be disadvantages during winter, because we also blocking the solar radiation for the winter period. So always that trade-off between hot and cold seasons, summer and winter periods, should be considered. And secondly, the vegetation is highly effective on outdoor thermal comfort. Firstly, trees. Of course, trees, they actually affect the against sky view factor in urban areas with their leaves. And they reduce the thermal radiation. They reduce the incoming solar radiation. So they create shaded areas. So as they create shaded areas, the many studies show that mean radiant temperature under the trees, as they shade the pavements, for example, so the mean radiant temperature are decreased. However, in some cases, when solar radiation is low or absent, trees in this case can behave as heat traps. So they trap long wave radiation, which is re-emitted from the pavement surface or building surfaces. So they may act as trapping elements. This may be also considered. And also in another study, 3 crowns are studied, and they found that cylinder-shaped 3 crowns reduce the heat stress more effectively compared to the other ones. For the vegetation, the leaf area index term becomes important. It is the ratio of the leaf area to ground cover. So higher leaf area index means denser leaves and greater ability to block the radiation, actually. Especially for the surfaces, vegetated surfaces, walls, floors, or roofs, etc. They reduce the long wave radiation because they reduce the surface temperature, so they reduce the re-emitted long wave radiation, and that this is really effective on the ambient temperature. Yes, and in a study, the researchers found that the surface temperatures, vegetated surface temperatures, may be like 24 Kelvin degrees lower than a normal or reference wall. So vegetation really decreases the surface temperature. And also vegetation has an effect on the wind patterns, especially trees. The trees, they have an effect to reduce the wind speeds. We have said that buildings also have that wind speed decreasing effect. However, buildings create high pressure and low pressure points, so they create eddies. However, trees, they have a much smoother decrease in wind speed. So in a study, again, the buildings in the neighborhood reduced the wind speed by 22%, and they added 77% coverage of trees, and the final wind speed reduction is reached up to 70%. And this wind effect actually, depending on the case, would increase the thermal comfort or decrease the thermal comfort. It depends on the other conditions, the temperature, solar radiation, etc. Again, another effect of the vegetation actually is transpiration. So through transpiration, they also decrease the temperatures around the leaves. So by creating shaded areas and by transpiration, the trees reduce the air temperature. However, we can talk about the green roofs. Green roofs, they have an effect of temperature decrease. According to a study, it can vary from 0.3 to 3 Kelvin in a city. However, to feel that cooling effect at the pedestrian level, the green roofs should be applied not higher than the 10 meters. So if the green roofs applied under the 10 meters, then we can feel that cooling effect at pedestrian level. Another effect of the vegetation, actually, through the transpiration and through the irrigation, they may increase the humidity, and humidity also is effective on the outdoor thermal comfort in hot seasons, and in hot areas, the higher relative humidities, higher humidity levels may also decrease the thermal comfort. Also, we have reflective surfaces. Basically, we can say that light color surfaces have reflects more solar radiation, absorbs less solar radiation, but dark color surfaces absorbs more solar radiation and reflects less solar radiation. And you can understand that in lighter areas, in lighter colored areas, the shortwave radiation is can be increased. However, depending on that reflection, the surface temperature can be decreased, but the long wave reflected short wave radiation is increased. Again, as the absorbed solar radiation is decreased, when the absorbed solar radiation decreased, then long wave radiation, so re-emitted radiation, is decreased by just the color of the surfaces. So cool materials, we can assume that cool materials also as a result of the reduced temperature surface, they decrease the convective heat transfer from the surface to the air, so they decrease the air temperature. Again, to feel that cooling effect at the pedestrian level, for example, if the cool roofs application, the roof levels should be lower than 10 meters to feel that cooling effect at pedestrian level. However, there is an important note that reflection, because light colored surfaces reflect back the solar radiation, and this would cause also results of glare and discomfort in visual area. We have also water bodies. Water bodies have generally, they are huge heat sinks and they absorb more solar radiation, but the surface temperature is not increased. So they have a cooling effect. Also, the evaporation from the water bodies also decrease the ambient temperature nearby, but this effects also depends on the water body's area, geometry, location, and the wind direction. Also, water bodies, we must say that they increase the humidity, and that increased humidity again may cause discomfort in some cases. And these are all the references that I used in this presentation. Thank you for listening.
Thank you very much, Ece.
Sorry if I'm too late for this.
No problem. I just have a comment. This geography, this part of the world has long forgotten the wisdom of the past architectural traditions. One example is actually coming to my mind from your presentation. You said that the streets that are perpendicular to the waterfront or wind direction, the predominant wind direction, is important in cooling cities. And actually, one of the first people that found this strategy was an ancient Greek mathematician, Hippodamus, from Miletus, so the Aegean city, Greek city. So it's a pity that we lost all this wisdom, and we have to catch up with new strategies and to remember the tradition of the past. Thank you very much for your presentation. Our last speaker of today is Mrs. Zeynep Gökçen Aşan. Her presentation title is Cool Up Program Towards Sustainable Cooling Solutions. The floor is yours, Mrs. Aşan.
Thank you. Thank you, Mr. Çakan. First of all, I would like to thank TTMD for giving me this opportunity, and also thank all the speakers previous made the presentations. They are all very informative. And also I would like to say that with the awareness of the responsibility of being the last presentation of the day, I will try to complete my part without tiring you too much. If you allow me, I will to share my screen. I hope you can all see the presentation right now. First of all, I'm working as a national coordinator within the Cool Up program for United Nations Development Program. I was working since 2010 with the Ministry of Environment, Urbanization and Climate Change under the umbrella of United Nations for studied on regulatory framework on F-gases, ozone depleting substances, and also greenhouse gas emissions. Currently working with UNDP Turkey team and continue to working in the field of sustainable cooling, focusing on natural refrigerants, alternatives, and nature-based solutions. Today, I would like to talk to you about a little bit our program, what we are doing in the country right now. So, Middle East and North African countries and Turkey also is facing a range of energy challenges against the visible effects of climate change due to the rapidly growing urbanization and heavily strained energy infrastructure. We are now in the region, cooling constitutes a major source of energy consumption, and it is expected to go further. In this context, a Cool Up program was launched in December 2020, and it is officially started in April 2025 and will conclude in January 2027. Our program brings together 10 international, regional, and national expert organizations in a consortium within the depth expertise on topics like ozone depleting substances, nature refrigerants, F-gases, energy efficiency, and buildings. Facilitate the transition to sustainable cooling is our approach. The project addresses the issue of sustainable cooling with a holistic approach, focusing on the cooling and air conditioning sectors in residential and commercial buildings by supported accelerated technologies changes within the scope of implementing Kigali Amendment and also Paris Agreement in Egypt, Jordan, Lebanon, and Turkey. Actually, we determine needs and objectives as political, financial, and technical support with an approach to refrigeration and AC in commercial and AC in residential buildings. Bringing together different worlds is our actually approach in efficiency and refrigerants, climate change, and protection of the ozone layer. Energy demand is, as all speakers are mentioning about, is to increase like 50% in 2040 in the MENA region, and countries facing a rapid range of climate change related challenges. The region's energy challenges include rapidly growing population, urbanization, and a heavily strained energy infrastructure. The use of cooling is expected to grow further, since with an improved standard of living, more households are using AC systems, and even additional climate impact comes from the refrigerants still used in many ACs and refrigerators. Such refrigerants with a high global warming potential are direct greenhouse gas emissions than carbon dioxide and nature refrigerants alternatives. What we are doing within the CoLab program right now is we are working upon pillars as policy by supporting implementation of, as I mentioned, Paris Agreement through NDCs and Kigali Amendment objectives. We are developing a national cooling action plan with contributions of all relevant stakeholders, including ministries and national associations. We are now developing measures to enable our country for implementing a better cooling impression and cooling and decreasing the emissions from cooling. And also we are trying to develop financial models and strategies to boost sustainable cooling, trying to support technology development by enabling nature refrigerants and energy efficient solutions to mitigate the rising cooling demand. CoolUp has also organizing capacity building and trainings for sustainable cooling. We are now trying to focus and raise awareness on safely working conditions and international and national implications on nature refrigerants. Organize several activities, several trainings for technical personnel in the field, and also try to increase information for policymakers, allow them to understand the current developments and market transformation. As I mentioned, cooling demand is driven by macro changes in socioeconomic factors such as population growth and household income, and environmental drivers such as increasing temperatures. Environmental and socioeconomic changes are macro changes that are considered external. As temperature increases, so will the demand for cooling as well. We are expecting as the population increases, so will the amount of people who require cooling in our region especially will increase. Also, incomes increase as the number of people who can afford the equipment will also increase. I would like to show you some results that we are doing, actually primarily results, what we are doing under NCAP National Cooling Action Plan right now. Within the National Cooling Action Plan, CoolUp team, we are trying to create different scenarios for emission reduction modeling for cooling, actually. Each scenario reflects a certain pathway for the cooling sector. These results are not yet finalized and still been discussing with the related ministries. But based on the collected technical and commercial data, we made several surveys within the market with most of the manufacturers in the country, associations, and also we use several data from different organizations and ministries as well. The market assessment provides the input for cooling sector scenario modeling, and therefore enables shaping national policies and roadmaps relating to energy performance for different type of equipment. To promote higher efficiency appliances, including maps, labeling, eco-labeling, nature refrigerants, consumer awareness and user education, and lots of capacity building for key stakeholders activities. As you can see, cooling, as I mentioned before, cooling demand is also increasing. Total emissions are expected to decrease in the business as usual scenario. Most relevant sectors like stationary AC and the commercial AC are using still F-gases. Total emissions shares across the sector are expected to stay relatively stable at the business as usual scenario. With another result, we do have a couple of results with direct emissions and indirect emissions that I'm going to show you. With direct emissions, business as usual scenario already exists 71% of emission reduction from 2020 to 2050. This considers the current F-gas regulation, Turkish F-gas regulation. And different aspects of stationary AC and mostly from multi-split, VRF, and single split units. Scenario 1 is respecting significant progress to decrease emissions by like 96% till 2050, but this considers the hypothetical NEF aligning with the current EU F-gas regulation, Turkish F-gas regulation, which requires a lot of placing on the market bans for ACs, for even commercial, for other appliances. And scenario 2 is almost zero emissions in 2050. We also did some calculations for indirect emissions. Indirect emissions businesses usual scenario projects 56% emissions in cooling demand, and it shows that this considers the grid factor decrease and technological improvements such as energy efficiency of the equipment. And scenario 1 goes to further and 68 emission decrease in 2050. This also takes into account introduction of demand response, financial incentives for highly efficient equipment, building retrofits, and tightened maps. Tightened maps upon considering EU. And scenario 2 assumes 100% emission decrease in 2050, which has more ambitious demand response measures after 2030, which assures carbon dioxide factor of electricity for rack systems is reduced zero by 2050. Meaning zero indirect emissions. This graph actually is taking the recent numbers obtained from the Ministry of Environment, Urbanization and Climate Change, and they reveal the current green certificate buildings according to EPC standards certificates. As a result of the current Turkish regulations, the number of Class C buildings are actually raising, but also you can see the increase in Class B and Class A buildings as well. However, emissions from HVAC systems are not presented, or natural refrigerant-based systems are not currently obligatory for consideration in these regulations. As besides all activities we're doing, we are also preparing some technical solutions catalogs and lots of papers within our program using the expertise of our consortium members, actually. We prepare a long list of technical solutions for Turkey, and for air conditioning and commercial refrigeration, we also, all of us very well aware that we do have lots of alternatives for those applications. Residential split air conditioning units are using hydrocarbons, and also flammable refrigerants are already in the market. Central hydrocarbon-based chiller solutions for hotel, larger commercial and public buildings are there. Also, central water-based cooling using water as a refrigerant is also an alternative. For commercial refrigeration, supermarket solutions using subcritical CO2 and hydrocarbons for freezers and refrigerators are already in the market. And transcritical carbon dioxide systems, freezers and refrigerators are also in the market and available. And for those, those technical and sustainable cooling solutions exist, and the majority of the technologies are early stages of the market, but still there. Cool Up, our program, builds an awareness about the benefits and potentials of sustainable cooling and refrigeration technologies by sharing implementation-based knowledge. We prepared a report, as I mentioned, on technical solutions for sustainable cooling in Turkey. Provides information about options for sustainable cooling. The report addressed stakeholders from different sectors, again, such as policymakers, financial bodies, but it's also addressed planners, manufacturers, and everyone who is interested. The key intention is to facilitate the uptake of sustainable cooling in Turkey with a specific focus on air conditioning and commercial refrigeration. Those analysis includes information on international cooling technology overview, AC and commercial refrigeration in Turkey, national good practices, and also suggestions for implementation sustainable cooling in Turkey. We do, as I mentioned, we do have several catalogs and regulatory analysis and also prospect studies concluded in our program. You can follow them under our website, and also you can email me if you have any questions related, any additional work you requested, and I would like to conclude my presentation here. Thank you.
Thank you very much, Mrs. Aşan. I know that TTMD is a supporting entity in CoolUp program. I wonder when the program will come to an end, will be terminated.
Actually, the program is expected to terminate in 2027. But we still need to, we have a lot of work to do, so I hope some other programs will conclude what we started.
I'm sure our participants who might be interested in having more knowledge about the CoolUp program can contact you, and we are glad to be a catalyst through this symposium for your program, actually. Thank you very much, all of you. It was really nice to hear each one of you. All the presentations were very informative, very high standard. Thank you very much, and hope to see you, and this time as listeners, participants, tomorrow, 1 p.m. on. So with these words, I wish you a nice evening and hope to see you tomorrow. Bye-bye.